In the last lesson, we have derived a formula of the electric field strength of a point charge. Let us review the formula first. For a point charge of quantity Q and a distance r from that charge, the electric field at that point is given by Q over 4 pi epsilon naught over r squared. Maybe we use this formula to deal with an example first. Consider two charges, one is at A and the other one is at B. Can you state the direction of the electric field at Y and at X respectively? Firstly, let us discuss how to find out the electric field at Y. We can consider the contribution of the field due to the two charges one by one. Firstly, consider the charge at A. Because it is positively charged, so the electric field at Y should be pointing to which direction? Good. Because the charge is positive, the electric field should be radially outward from the charge. So, at Y, the electric field due to the charge at A should be pointing to the left. What is the electric field due to the negative charge at B at Y? Good. Because the charge is negative, the electric field due to the negative charge should be radially inward. So the electric field at Y due to the negative charge should also be pointing to the left. Thus, the resultant field at Y due to the charge at A and B should be pointing to the left. How about the electric field at X? Very good. The electric field at X due to the positive charge is pointing in this direction. And the electric field due to the charge at B, the negative charge, should be pointing in this direction. Is it okay? Because the electric fields are vectors, we have to find out the resultant of the electric field of these two vectors. So you can resolve the field into two components. So we may notice that the vertical component of the fields cancel out each other. So the resultant field at X should also be pointing to the left. Apart from the direction of the electric field, can you calculate the magnitude of the electric field at Y? Okay, let's do it right now. The electric field at Y should be the sum of the electric field due to the charge at A and at B, because the direction of the electric field are both pointing to the left, the same direction. Please notice that the sign of the charge at B is no longer need to be considered, because we have considered the direction of the electric field due to the negative charge. So, how to find out the electric field at Y? We can deal with the charge one by one. For the point charge at A, the electric field at Y is equal to the quantity of the charge, 2 times 10 to the power minus 8, divided by 4 pi epsilon naught, and then the square of the distance. What is the distance of the charge from A to Y? It is equal to 15 cm. So it is equal to 15 times 10 to the power minus 2, and then take the square. It is the electric field due to the positive charge at Y. How about the electric field due to the charge at B at Y? Because the two charges are of the same magnitude and same distance from Y, so the magnitude of the field due to the negative charge at Y should of the same magnitude. So we simply just multiply 2 in this expression, then you can find out the resultant field. So the value is equal to 1.60 times 10 to the power 4 Newton per Coulomb. How about the electric field strength at X? This one seems to be a little bit difficult because the two electric fields are not in the same direction. It is a sum of two vectors. We can also deal with the charge one by one. Firstly, we consider the positive charge at A, the positive charge A first. What is the electric field at X due to the charge at A? So we use the same formula. The quantity of charge, 2 times 10 to the power minus 8, divided by 4 pi epsilon naught. What is the distance from A to X? By considering this right angle triangle, the height is 15 cm and the base is 15 cm too. So the hypotenuse should be root 2 times the height of the triangle. So it is equal to 15 cm and then times root 2, and don't forget to take the square of the distance. This expression gives the magnitude of the electric field at X due to the charge at A. But we all know that the resultant field is only contributed by the horizontal component of this field. So we have to find out the horizontal component of this electric field. What is the angle of the vector to the horizontal? Because this triangle is an isosceles right angle triangle. So this angle should be equals to 45 degrees. The horizontal component can be found out by multiply cosine 45 to this expression. So it is the horizontal component of the electric field due to the charge at A at X. And what will be the resultant field due to the two charge? Because by similarity, the horizontal component of the field due to the negative charge should have the same magnitude. So simply multiply this expression by 2. Then we can find out the resultant field at X, which is equal to 5.66 times 10 to the power 3 Newton per Coulomb. Is it clear? So it is the time for you to try out some question first. Can you do the question on page 29, 1 and 2? Apart from the electric field of point charges, can we find out the electric field of a conducting sphere? So it is not too difficult. Consider this sphere of radius r. If quantity of charge Q is distributed over the surface of this conducting sphere, so can you find out the electric field strength on the surface of this conducting sphere? As we have mentioned before, if the charge are uniformly distributed over a conducting sphere, then we can regard all the charges are concentrated at the center of the sphere. So the electric field is also given by this expression. Just consider all the charge are concentrated at this center. How about the electric field on the surface of the conducting sphere? So we simply put the small letter r, this variable, by the capital letter R, the radius of the sphere. So the electric field strength on the conducting sphere is given by this expression. But what is the theme of this part of the discussion? Look at the expression first. We are going to rearrange some of the terms. Take out the constant 1 over epsilon naught first. And what are the terms left behind? Good. It is the charge divided by 4 pi R squared. Anybody notice this expression? What is this expression represent? Yeah, it is the surface area of this conducting sphere. So, this expression can be represented by this formula equals to 1 over epsilon naught times Q over A. What is meant by Q over A? It is the charge per area, or we can use the term surface charge density sigma to represent this term. Notice that this expression is derived from a conducting sphere, but actually it is a general expression of the electric field on a conducting surface, no matter what the shape or the look or the dimension of the conducting sphere. This expression can be used to find out the electric field strength on the conducting surface. In the DSC syllabus, apart from the electric field of a point charge of a charged conducting sphere, we have to deal with the electric field of parallel plate. What is a parallel plate? A parallel plate is two large metal surfaces of area A separated by a small distance. If charge Q and negative Q are distributed over the surface, and if the separation is small, then we know that the electric field can be represented by this diagram. And this diagram, we notice that if the edge effect can be ignored, the electric field is uniform. But do you know how to find out the electric field strength between the plates? Yeah, it is a bit difficult, but doesn't matter. We don't know how to find out the electric field between the plates. We can consider this point first, a point on the conducting surface. Do you still remember the electric field of a conducting surface? Yeah, we just discussed this expression before. Can you find it out? Good. The electric field of a conducting surface can be expressed by sigma over epsilon naught. Do you still remember what is sigma represent? Yeah, if the plate is of area A and charge Q distribute over the surface, sigma represent the surface charge density, or the quantity of charge divided by its surface area. So, the electric field at this point, the green point, can be expressed by this expression. But you may have a question. We are going to find out the electric field between the plates. Then, can we find out this formula? Yes, because the electric field between the plates is uniform. What does it mean? That means the electric field at any point over this volume is the same. So the electric field on the surface is equal to the electric field between the plates, or any point between the plates, because the field is uniform. So the electric field between two parallel plates is given by this formula. Let us take a look of all the formula first. The electric field of a point charge is given by Q over 4 pi epsilon naught R squared. The electric field between two parallel plates is given by Q over epsilon naught A. So, can you, using these two formula, to do some question? Can you do the class practice on page 9, question 1 to 10? Apart from the electric field between parallel plates we have just derived before, we can derive another expression for the electric field between two parallel plates in terms of the electric potential. Let us review the three important formula: the electric force between two charges, the electric field of a point charge, and the electric field between two parallel plates. And this expression can be expressed in terms of the electric potential between the plates, which is given by V over D, where V is the electric potential between the plates and D is the separation between the two plates. Maybe we can use this formula to find out the electric field between two plates. Suppose two parallel plates of potential difference between them 3 kV. Firstly, can you tell me the direction of the electric field between the two plates? Yeah, the electric field should be pointing from the positive charge to the negative charge, which is pointing downwards. And what is the electric field strength between the two plates? You can use the formula electric field is equal to the electric potential divided by the separation between the two plates, which is equal to 3000 divided by 1 cm. Don't forget to express the separation in terms of meter. So the electric field strength is given by 3 times 10 to the power 5 volt per meter. These are all the formula of the electric field between the conductors. So, can you try out all these questions at home? And we will discuss this question when we have class at school later. Goodbye and thank you.